Hi dear students, this presentation is from the second module of the subject Advanced Energy Engineering. In this system we will be discussing about the solar photovoltaic system, that is a system in which the solar energy is directly converted into electrical energy. Photovoltaic energy conversion, or simply PV conversion, is a direct conversion technology that produces electricity without the use of a thermodynamic cycle or a working fluid. See, all the earlier systems we were using either a thermodynamic cycle to produce the power, or some working fluids were there to abstract the heat energy, but there is no such system, there is no such things in this system, that is known as solar photovoltaic system. The basic unit of a photovoltaic system is the photovoltaic cell, also called the solar cell. So solar cell is the fundamental unit of the photovoltaic system, and this solar cell directly converts solar radiation into electricity. This cell is actually converting solar radiation into electricity. It is based on the photoelectric or photovoltaic effect. Coming to the photovoltaic effect is the generation of a potential difference at the junction of two different materials in response to electromagnetic radiation. See, based on the electromagnetic radiation, at the junction of two different materials, some photovoltaic effect is generated, or voltage is generated. That is what is known as the photovoltaic potential difference is generated. That is what is known as the photovoltaic effect. So there should be a combination of two different materials, and solar radiation also should be there, electromagnetic radiation also should be there. So if all this comes in the desired condition, then what happens is a potential difference is created at the junction, and this will cause for the production of the voltage or electricity. This effect is exhibited by material called the semiconductors. Usually the materials which exhibit photoelectric or photovoltaic effect is known as semiconductors, and an example for the semiconductor which producing this effect is silicon. Okay, coming to the principle of the solar cell, very thin silicon slices called silicon wafer is the heart of the photovoltaic cell. See, actually the thickness of this cell is very thin. It is thickness is very less, and just like slices, okay, very thin silicon slices called silicon wafer is the heart of the PV cell. Silicon atom, coming to the structure of the silicon atom, it has four outer electrons which are weakly bound to the nucleus of the atom called the valence electron. See, in the outermost shell, that is in the valence shell, the silicon is having four electrons. See, if a silicon, normally these electrons are bound with the electrons of the other silicon atom to form covalent bond, and hence no freedom of movement. See, if one silicon atom is combined with another silicon atom to form the continuous structure of the silicon, what happens is these four free electrons at the outermost shell, that is valence electrons, will combine with the other four electrons of the nearby silicon atoms. So all the atoms will be forming a covalent bond with the other electrons from the silicon atom. So no electron is free to move. That is the basic structure of the silicon. Okay, if the silicon is doped, then what is doping? If the silicon is doped, actually doping is the introduction of the impurities into the semiconductor crystal to change its conductivity. So if you are adding a impurity to the crystal of the silicon, then its conductivity will change. So which impurity is adding, its conductivity is based on which type of impurity is adding. We will discuss this in detail. With a small quantity of element that has 5 valence, assume that if we are doping with an element, a small quantity of element that have 5 valence electrons. See, silicon is having only 4 valence electron. We are doping with an element having 5 valence electron in an atom. It can fit into the silicon crystal structure such as phosphorus or arsenic. See, the atoms having 5 valence electron is phosphorus or arsenic. So we are adding this phosphorus or arsenic into the silicon crystal. So we know that silicon is having only 4 valence electrons. So these 4 valence electrons will form a covalent bond with the 4 valence electrons of the phosphorus or arsenic. So definitely one electron will be free to move. Okay, one electron will be there without bonding. Some extra electrons are created as the fifth valence electron does not create a covalent bond. Such a doped material is called the N-type semiconductors. So silicon doped with 5 valence electron element, then it is called a N-type semiconductor. Such a semiconductor formed is known as N-type semiconductor because the extra electron carry negative charge. The reason for why it is called N-type semiconductor is the extra electron always carries negative charge. On the same time, think about alternatively, if the silicon is doped with an element that has only 3 valence electrons, think about this condition. The silicon is doped with the element having only 3 valence electrons. The example for 3 valence electron element is boron or gallium. So what happens is while forming the combination, silicon is having 4 valence electron, but arsenic is having only 3. So 3 element of the arsenic will form covalent bond with the 3 electrons of the silicon. So one hole will be always left in the crystal lattice. Okay, absence of an electron in the covalent bond or holes are created. So this will lead to the creation of the holes. This type of semiconductors are called P-type semiconductor. From this figure you can have a clear idea. See, this one is the phosphorus impurity added or doped element is this one, phosphorus. All others are silicon. So you can see the 4 elements of the phosphorus, see 1, 2, 3, 4, all the 4 have made covalent bond with the at least one element of the silicon which is near to this phosphorus atom, but you can see one extra electron free in the lattice. So this is a free electron in this type. That is, this type of semiconductors are called N-type semiconductors. Whereas here if the doped element is having only 3 electrons, so you can see this one is the boron element added as an impurity. So the 1, 2, 3, here is the 3 element of the 3 valence electrons of the boron which is combined with forming covalent bond with the silicon element. C1 here, 1, 2, 3. So here you can see there is no electron to make a covalent bond for the electron of the silicon with the boron. So one hole is created here. See, this is the missing electron, or simply we will call it as hole. Missing electron or hole. So this type of semiconductors are called P-type semiconductors. Okay. In N-type semiconductors, if sufficient energy is provided, the electrons will move freely. That we already know. If free electrons are given some excitation energy, then it will move to the next level. So similarly, if the incident radiation is able to provide some energy, then the electrons will move freely, but the direction of the movement is random. See, if you think about the N-type semiconductor only, so if the radiation comes and hits the N-type semiconductor, this will give the energy to the free electron, so that the free electron can move freely within the lattice. But we cannot assure a unidirectional flow. The electron movement will be random movement. Okay, so we cannot assure a unidirectional flow. For producing current, we require a unidirectional flow of electrons. That is what is we required. So no electricity is produced. Since the movement of the electron is random, no electricity is produced. So to make the electron flow unidirectional, what we will do is we will be creating a junction of both that P-type semiconductor and N-type semiconductor. We will create a PN junction. Once they are joined, the free electrons from the N side will migrate to the P region to fill the holes. This way a depletion region is formed where there is no free electrons and hole. I will show you the figure here. See, this is N-type semiconductor where we have a lot of negative electrons. Electrons are free to move in this region, N-type semiconductor. Here we are having P-type semiconductor where the majority are holes. Okay, plenty of holes are available here, plenty of free electrons are available here. This is the depletion region. So once these two form a junction, N-type and P-type form a junction, what happens is the electrons from this side move towards the P junction, P-type semiconductor, to combine with the hole. Similarly, the hole will be moving towards the N-type to form a combination with the electron. So mutual movement of the both hole as well as the electrons will be there. So this will take place from the junction itself. Initially it will be taking place from the junction itself. So within that junction, in a small area, we can see the electrons might have moved to the other side and holes might have moved to the other side. So a depletion region is created as the time goes on. This region is the depletion region. So in this region right now there is no electrons as well as the holes. So this region having no electron and hole is known as the depletion region. Actually it is happening once these are joined together. So before joining there is no depletion region. Once p and n junctions are formed together, then after a particular time this depletion region is created. Okay, so now what happens is after that also there is a tendency for the electron to move from this side to this side and hole to move from p side to the n side. But since there is a depletion region, here we have negative electrons concentration more. So at this layer of this depletion region, at this boundary we will have a negative charge. Here we will have a positive charge. So this will repel the electrons to move from this side, and the positive charge created at this layer will repel the holes to this side itself. So no more crossing of the electrons or hole in the depletion region is not possible. So there is a potential difference is created within this depletion region. That is what is required for the unidirectional flow of the electron. So what happens is if you are connecting a load to this one, so what happens is if a load is connected, so the electrons will move along this load to the hole region. So by this way we can assure a unidirectional flow. That is the working principle of the solar cell. To make the electron flow unidirectional, a driving potential is needed. The easy way is to produce a p-n junction. Once they are joined, the free electrons from the n side will migrate to p region and fill the holes. This way a depletion region is formed where there is no free electrons and holes. Due to the migration, n side boundary becomes slightly positive charged and p side boundary becomes slightly negatively charged. Hence an electric field is created which provides the driving potential. See, the electric charge created between these two boundaries. See here negative charge and here positive charge. This electric charge created at the boundaries will create the potential difference. The n region is the upper layer where the light falls. See, coming to the solar cell, the n region will be the upper layer and p region will be always the bottom layer. So in this layer the light rays will be falling. See, solar radiation is coming and it is falling on this layer. Once the solar radiation reaches the depletion region, what happens is by absorbing the photon energy of the light ray, the electrons and hole pair is created in the depletion region. See here both the boundary, here we have negative charge, here we have positive charge. So the electrons will be always expelled to this side, n side, and the hole will be always expelled to the positive p side, okay, due to the electric charge or the potential difference created here. So the n region is the upper layer where the light falls. Once the light reaches the depletion region, penetration through the n, it penetrates through the n layer. The photon energy of the solar radiation is sufficient to create an electron hole pair, but the electric field in the depletion region drives the hole and electron out of the depletion region. Why it is doing so is due to that negative and positive charge at the boundaries. So always whatever electrons and hole is created at this depletion region will be driven out of the depletion region by this potential difference. Hence an electron concentration on n region and hole concentration in the p region becomes so high that the potential difference is developed between the two. As soon as a load is connected, the electron will pass through the load and will combine with the hole. In this way, PV cell continuously gives the DC current. Okay, to increase the performance of the photovoltaic cell, the top N layer is made as very thin and heavily doped, whereas the P layer is made as very thick and lightly doped. This will increase the width of the depletion layer and more electron hole pair is generated. So by making the N layer very small, very thin and heavily doped, and P layer very thick and lightly doped, what happens is more depletion region is created. The width of the depletion region created will be more. So more electron hole pair can be created by the incident solar radiation. So more the number of electron hole pair is generated, more the voltage that we can get it as the output. This results in the more power generation. Another advantage is with thin N layer, more light can reach the depletion layer. That is the another advantage of making the N layer thin. A single solar cell produces around 0.5 volt and 3 ampere. That is the standard. Okay, so number of cells connected in series, that is what is known as module. will increase the voltage, whereas if connected in parallel will give more current. Okay, so a number of solar cell connected in a connected in series is called module, and lot of modules connected is known as array. Okay, we will call it a solar array. Okay, that is all about the basic principle of the photovoltaic cell. In the next presentation, we will be discussing about solar photovoltaic power generation system, how the power is generated in this photovoltaic system. Okay, thank you.